Okay, so today we're going to talk to you about our part that we selected for materials analysis, the Opinel knife blade. In the group T8 is Peter Hudlicka, Tyson Norris, and Nicolas Vrban. Enjoy.
The Opinel is a traditional French pocket knife with a simple utilitarian design that has been used for over a century to perform everyday utility chores, kitchen duties, wood carving, and for camping crafts. From humble origins in rural France, the Opinel company now sells approximately 15 million knives a year throughout the world and has become symbolic of French culture.
Now we're going to talk to you a little bit about the part we selected, the current design of the part, and the environment in which it's meant to be used. The part, as already mentioned, is a number 8 Opinel Carbon Steel pocket knife blade. The focus of this design currently is to mitigate the corrosion and improve the wear resistance of the blade. The reason for this is that it's primarily meant to be used in outdoor environments, whether that means hiking, camping, generally the wilderness, but also DIY projects and then everyday home, school, and work use. The current design features a wooden handle into which the carbon steel blade can fold safely and securely. The blade pivots out from the handle on a pivot pin that's housed in an assembly cylinder. This assembly cylinder and the pivot pin are then enclosed by the locking mechanism, which can both secure the knife blade upright as well as secure it when it's folded into the wooden housing. One of the primary flaws with this knife blade design is that it's highly susceptible to corrosion. This is especially apparent in high carbon steels, especially those that don't have a high alloying content. The primary mechanism by which corrosion acts is through crevice corrosion. You can see this in the bottom left-hand corner in the locking mechanism, where small gaps create a gradient in concentration, allowing for ion transfer and consequently the formation of rust. Pitting corrosion can be seen in the top right-hand corner, all along the surface and in the fillets of the blade. This is usually due to an unpolished finish or a worn surface. Concentration cell corrosion is the underlying mechanism of the above two methods mentioned, and it can be simply formed by having water left on the blade, which isn't uncommon, especially in outdoor environments. Microbial corrosion can also form and can attack the metal both chemically as well as electrochemically. Galvanic cell corrosion isn't seen too much on this knife because of the use of similar metals.
The high carbon steel of the traditional Opinel has excellent mechanical properties, but is highly susceptible to the formation of rust during everyday use. A traditional method of protecting carbon steel knives and tools, called bluing or forcing a patina, has been employed on our selected Opinel. A patina is a dark oxide coating formed when the carbon steel is exposed to an acidic solution, but offers only moderate protection to corrosion. For this Opinel, it was placed into a vinegar solution with an estimated pH of 2.4, which promoted the formation of Fe3O4, the mineral magnetite, coating the surface in a powdery, almost black coating. Through a slight passivation effect, this offsets the formation of much more damaging Fe2O3, the mineral hematite, the classic rusty red color, which experiences a significant volume change resulting in the flaking and continual deterioration of the metal. In addition to the formation of the semi-passive magnetite, it is possible that the acidic solution enabled the formation of more highly passivating coatings from alloying elements within the steel, most notably manganese or silicon.
Now we're going to talk about the design specifications of our knife. The primary functional requirement was that the blade must be able to cut through most materials found in its environment. That means wood, rope, tape wire, etc. The constraints were split into two categories: primary constraints, which directly had equations tied to them used to calculate the MPI, and secondary constraints, which were either qualitative or part of the primary constraints, but didn't have an equation tied directly to them. Minimizing mass by minimizing thickness was the primary objective. We kept width and height of the blade constant and minimized thickness by using equations for lateral bending and for stress. For lateral bending, a maximum deflection of 1/4 of a millimeter from a 20-pound force load located 4 centimeters away from the pivot point of the knife was used. For stress, we said that the blade could not yield under the impact load of a 95th percentile male in the form of a point load located 4 centimeters away from the pivot point of the knife. The 20-pound force load was qualitatively assumed to be that of applying a load when you're cutting or carving using the knife, and the 95th percentile male was just used as an upper bound for a maximum amount of force that might be applied to the blade. Minimizing cost and minimizing corrosion were applied to the MPI after this calculation was done to further reduce the pool of materials that we had available to us.
As seen in the blade diagram, a force of 1020 newtons is applied to the blade 40 millimeters from the pivot. Using a torque equilibrium equation, a resultant internal force of 4,800 newtons was calculated, perpendicular to the applied force. This results in tension in the blade and allows for a stress calculation, wherein the yield strength is calculated using the perpendicular force, the cross-sectional area of the blade, and geometry-specific constants including a predetermined C value and the radius of the pivot hole. This stress equation can then be put in terms of the free variable, thickness. This rearranged equation can be subbed into the mass equation, allowing for density and yield strength to be separated from the geometric and functional requirements in the equation. Using 100 grams as a maximum, a threshold line with a slope of 1 was then created, eliminating many materials from the selection process. Ideal materials for requirement 1 were then limited to those that surpassed the threshold while maximizing yield strength and minimizing density. For requirement 2, a force of 85 newtons is applied sideways to the blade, 40 millimeters from the mounting. This is shown in the blade diagram in the top left. This force would bend the blade, causing a displacement that is constrained at 1/4 of a millimeter. This displacement can be understood in an equation that uses the dimensions of the blade, the applied force, and Young's modulus. This formula can then be put in terms of thickness and subbed into the mass formula. The MPI is then isolated as Young's modulus and density, allowing for an additional threshold line with a slope of 3 to be created. Ideal materials were then limited to those that satisfied requirement 1 while also passing requirement 2's threshold, and which maximized Young's modulus while minimizing density. After both requirements were calculated and materials were eliminated, the selection pool was further narrowed by adding in additional limits. These were a minimum hardness, minimum durability ratings in fresh and salt water, the ability to be metal press formable, and a maximum price. These limits were added to eliminate unpractical materials such as wood, to better comply with industry standards in manufacturing, and to aid in other practical concerns such as corrosion resistance and cost. From the material selection process, the ideal chosen material was determined to be AISI 440C stainless steel. This material was selected due to it being comparable in terms of strength and density to other high-end candidates, while also providing excellent durability in both fresh and salt water. This would allow the stainless steel to operate effectively and maintain that standard in all of the knife's typical operational environments. The chosen stainless steel does not match the blade's actual material, AFNOR XC90, a high carbon steel very similar to another potential candidate, AISI 1095. 440C offers numerous advantages over 1095 with higher strength, higher hardness, and a higher elastic limit, all while having very comparable density and far better corrosion resistance. However, 440C's greatest performance is traded off by its nearly doubled cost.
The 440C steel arrives from the factory in a soft annealed form, which could be achieved by holding the rolled steel at an austenitic temperature until homogeneous and then allowed to slowly furnace cool, resulting in the formation of a coarsely grained pearlite. This soft microstructure allows for the high degree of machinability needed to shape the blade. After machining, the blade's final mechanical properties can be determined by applying the following heat treatment process. In the first step, the blade must be preheated to a temperature of 815 degrees Celsius, just below the austenization temperature, for 30 minutes. This allows a uniform temperature to be achieved throughout the steel in less time during the next step, which results in less grain growth and a finer microstructure. The second step is to raise the temperature of the blade to 1040 degrees Celsius, or just above the austenization temperature. In this step, the iron microstructure changes from BCC to FCC structure, with increased solubility to carbon and other alloying elements, and permitting the even distribution of these elements throughout the material. The austenitic steel is removed from the furnace and allowed to cool in air until room temperature. Due to the alloying elements of the 440C steel, this cooling rate is sufficient to form a martensitic structure. Due to the high carbon nature of the steel, however, small pools of retained austenite are also formed throughout the material. The fourth step is a cryogenic quench from room temperature to negative 130 degrees Celsius for several hours. This deep freeze of the steel allows for a higher percentage of the retained austenite to transform into martensite. At this point in the process, the blade is extremely hard and brittle.
Now in this short video you can see cryogenic quenching occurring from knives that have already been removed and cooled to room temperature from heat treatment. You can see this blade being inserted into an ice bath that has acetone added to it to further cool the water. These knives will be left in solution for about 2 hours while they cryoquench, and once removed, they'll be significantly harder.
Finally, a double temper process will be performed in order to improve the impact resistance and ductility of the metal. The blade will be raised twice to 200 degrees Celsius for 60 minutes each and allowed to cool in air to room temperature in between. This allows the metastable martensite to release a uniformly dispersed precipitate throughout the structure. The first temper effectively softens the martensite of the quench, but promotes the formation of new martensite within the retained austenite, which requires a second temper to soften. After the double temper, the heat treatment process is now complete, and the blade has a hardness of 59 HRC and maintains a higher degree of strength and ductility.
Coatings can greatly increase the wear resistance as well as mitigate corrosion in knife blades. Powder coating, physical vapor deposition, and polishing are the three methods traditionally used in industry. Powder coating being the most common used because of the fact that it maximizes on all three parameters, cost, corrosion mitigation, and wear resistance, can be seen in the top right corner in this military use knife. One downside of powder coating is that it can sometimes impede sharpening of the knife. Physical vapor deposition, or PVD, has fantastic mitigation of corrosion as well as wear resistance, and is often referred to as a DLC, or diamond-like finish, in the industry. Unfortunately, it's quite expensive, which makes it less used. Polishing is fairly cheap, and it mitigates corrosion very well, but it doesn't improve wear resistance all that much unless you're polishing very, very frequently. Corrosion mitigation is done by eliminating the wear that can cause pitting corrosion on the blade.